before we talk about threads, I'm going to talk about green threads, which is, and I don't know that this Python 3 web server uses green threads for certain, but I know that green threads are common in both Python and Ruby. So a green thread is when, I suspect, I won't have us all do this again, but I suspect that this is using green threads. I didn't have enough people to test, but a green thread would be that the process execution stops and lets another bit of process go for some amount of time, and then switches back and forth on a single thread. And so in the example of our web server, I could click on download this and it would download at full speed. Then when someone else clicked to download it, it would occasionally halt my download and then start their download or resume their download. And then it would halt their download and resume my download. And so it would be able to handle multiple clients, but it wouldn't be able to do more than one thing at a time. It would look like it's doing more than one thing at a time, but it actually wouldn't do more than one thing at a time. The work that gets done would be limited to a single thread. It would just not wait until the task is complete before it switches to the next thread. So that's what green threads are, and they are common in languages like Ruby and Python because it allows you to have multiple requests be handled. And if you actually run multiple processes or multiple forks, then everything appears to run faster because more things are being handled simultaneously, even though they're not necessarily being handled actually simultaneously. So I don't know if that's a perfect explanation, but the gist of green threads is it looks like multiple things are happening at the same time, but really it's one single thing and it just switches back and forth occasionally. Any questions on that? Okay. So now let's talk about actual threads. So with actual threads, what you have is within a process, basically a thread is more or less, say, a function. And that function can call other functions. And that function is potentially going to run on the same core as other functions, but it might run on a different CPU core. So with threads, we can actually have as many things happening exactly at the same time as we have CPU cores or CPUs or combinations of CPUs and CPU cores, depending on the architecture. On most of the virtualization that we use today, like DigitalOcean and AWS and Azure, et cetera, the virtualization environment that we will use will consist of multiple, one or more CPU cores, but probably not more than one actual CPU. If the physical hardware has more than one actual CPU, it'll be represented to the environment that we're paying for as multiple cores, and there's some capping and stuff that goes on. And on your desktop computers, they all typically have 4 cores these days, but you can have like 64 cores or hundreds of cores, and the more expensive, you know, a CPU server is, the more cores it'll have on each CPU die. So, and threads operate similarly to processes. They can operate independently, but they share memory with the process. So within the process, if the value X is 42, every thread that reads that is going to get 42. And when the value changes to 37, every thread that reads that value is going to get 37, because it's all in the same group of memory. And this Nginx like I said before, well, it specifically uses the event loop pattern, but it took advantage of threading to get much higher performance. And that's why, it's been a replacement for Apache, and the web servers that have come out since Nginx are similar. They, rather than having a full process that takes up as many megabytes as the original process, they just run threads, and the threads are lighter. So if you look at a node process, like this is a screenshot from a server I've got that runs a web server that I have codenamed Goldilocks, and an application server that I've codenamed Walnut. And you can see that there are like, well, 1 billion of these node processes. And if you look up top where it says tasks 44, that means number of processes, 93 threads, and only 1 is running. So everything else is sleeping, 1 is running, but there's 93 of these. I think it might be 93 of the node processes itself. But these are not, when you look at a tool like this, most often when you see a bunch of something, it's not processes of that thing, it's threads of that thing. So some of these threads, well, in this case, most of them are just sleeping. They're just waiting for something to do. The function that was running is basically complete, and it's waiting for a new function to run. So Node uses threads, and the thread model, it uses less memory, and it doesn't have the same problems with IPC. So why do we need something better than threads? Well, they're lightweight, but they're not super lightweight. They're about 2 megabytes each. So again, threads don't scale. You can't have, if you have 10,000 people connecting to your website, well, then you need 20 gigs of RAM, which isn't necessarily hard to come by, but it still doesn't scale well enough. It uses too many resources, and you have the problem of data races, which is one thing that we don't usually have to deal with in Node, or the ways that we deal with it in Node are very different and more safe. So a data race is basically, I keep on giving this example of x equals 47 and x is changed, and now x equals 37. Well, since 2 threads can actually run simultaneously, even if it's on a single CPU core, this is still a problem. But it's even more of a problem when there's multiple cores, because threads, just like green threads will halt and switch back and forth, that green thread model is based off of the actual thread model. So threads can halt and then go back and forth. In the case of multiple CPUs, or CPU cores in particular, you can have 4 threads that are actually running, 4 functions that are actually running code at the same time. So if one of your functions changes the value of x, that operation may not be atomic. So it could be in the middle of changing the value of x from a big number, like 4 billion, to a small number, like 3, and another thread could read as one of those bytes is updated before the other byte has updated. And in that case, you can get corrupt data. One of those threads, instead of getting back the old number, 4 million, or the new number, 3, could get back basically a random number, because the CPU, one of the CPU cores was in the process of changing the memory in RAM as it was being read. And likewise, you can just get unexpected behavior, because between 2 lines of code, let's say line 1 is x equals 42, and line 2 is x plus plus, between those 2 lines of code, that thread could have either been put to sleep, and another thread given priority, or another core could have simply run its executions faster. And if there was another function in your program that modified x in some way, then after line 2, if you were to print what is the value of x, instead of getting that x incremented from 47 to 48, you could get some random unexpected value. So this is one of the problems with threading, is that while it's lighter weight and it's more convenient to use, it it introduces new types of problems. Now, if people are on the functional bandwagon, they're going to tell you functional is better, blah, 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 because, you know, this problem isn't a problem because the programming language itself constrains you in such a way that you can't have this type of problem. And that is true. The only problem with functional programming is that anyone who's been able to understand it loses the ability to explain it to others. So you should definitely I advise anybody to look into some of the reasons behind pure functional programming and some of its advantages and whatnot. More and more, we're seeing functional patterns come into what were maybe traditionally non-functional languages, and these are good patterns, but it's problematic to. It's just not the hammer for every nail. Okay,